What are the odds? Odds, or probability, is a way to refer to how likely an uncertain event is to occur. A simple coin flip has 1 over 2 odds of being heads or tails. Getting a 6 from rolling a 6-sided die is 1 over 6. Where do these numbers come from? These numbers are quite intuitive, as they are simply the number of possible outcomes that you want compared to the total number of outcomes. This way of thinking is the basis of all probability calculations. However, once we start to examine more complicated situations, for example the odds of rolling 10 6-sided dice, and their sum being less than 35, this way of thinking will create a long-winded process. If we try to calculate a similar example using only 2 6-sided dice, rolling a sum less than 7, then we can immediately see the time-consuming problem. Not all possible sums are uniquely obtained. If we create a square using the results of the first die and second die as 2 side lengths, we can create this probability area, where each small square shows the sum of the 2 results, and each small square has equal probability. We can see since each die has 6 possible results each, this makes 36 different possible rolls. When we add up the results, we instead see that there are only 11 uniquely possible outcomes. If we try to apply a similar reasoning from last time, we would say a 5 over 11, or 45% chance of rolling less than 7. Since there are actually 36 total outcomes, the odds end up being 15 over 36, or 42%. An important detail we can revisit later is that if we add up the probabilities of all uniquely possible outcomes for an event, it should be 100%, since it accounts for all possibilities. You can think of it as asking the question, what are the odds that an event occurs and any outcome happens? For example, when you flip a coin, what are the odds of getting heads or tails? Both are 50%, and 50% plus 50% is 100%, assuming it doesn't land on its side. This concept of analyzing the number of different possible ways for a unique outcome to occur is widely used in probability, and is known as permutations and combinations. The main difference between these two terms is that permutations cares about the order that the events happen in. For example, which result of the die roll was first, while combinations does not. These two have a wonderful simplification of the above problem we did, and any related ones. The equations you can see show up on the screen where P of NR is permutations, and C of NR is combinations. The exclamation mark is known as a factorial, for those who don't know. And N is the number of possible outcomes per event, and R is the number of events. For those who don't know, a factorial is a mathematical operator that multiplies all whole numbers up to and including the number inside the operation. So 5 factorial is equal to 1 times 2 times 3 times 4 times 5, which is 120. The main way this is helpful is that we can simplify very large and complex situations into a single formula, instead of creating a probability square, or cube, or tesseract, or you get the point.
Permutations and combinations make a great simplification of a simple type of probability known as the binomial distribution. Binomial meaning 2 terms, or in the case of probabilities, 2 outcomes. This is a type of analysis where we ask the odds of a repeated outcome occurring n times after m trials. We can technically make anything binomial if we know its unique probability by just viewing the 2 outcomes as the event happens or the event doesn't happen, which according to our talk about sum of probabilities earlier should add up to 100%. The general way you write a binomial distribution is m factorial divided by both n factorial and m minus n factorial. You then multiply this by a to the power of n and b to the power of m minus n, where a is the odds of the event happening, and b is the odds of the event not happening. So a plus b should add up to 100%. You will notice we use combinations instead of permutations for this. In general, we don't care about order when doing distributions, as considering order tends to be very case-specific and requires a specialized approach. In Pokemon, shiny Pokemon are an incredibly rare phenomenon that some people have never once encountered despite playing many hours of Pokemon games. Unless you play Pokemon Go, Scarlet Violet, or Legends Arceus, in which case you are probably swimming in shinies, as they are much easier to get for many different reasons. From conception in Generation 2, when color was invented, the odds of a shiny Pokemon being generated is 1 in 8,192. Wow, that is low. For context, that is around the odds of flipping 13 coins and they all land on heads. Fret not, as Game Freak took pity on us and increased these odds to 1 in 4096 in Generation 6. So now you only need to get 12 heads. Much more doable. There are two intended ways to improve the base odds of receiving a shiny Pokemon in the old Pokemon games. Let's simplify to Generation 6 and behind. The first was introduced in Generation 5, Black 2, White 2, known as the Shiny Charm, which was a reward for catching all Pokemon in the National Pokédex. RIP to the National Dex. This roughly triples the odds of a shiny Pokemon being generated, around 1 in 2731 for Gen 2 to 5, or 1 in 1365 for Gen 6 onwards. It does this by re-rolling twice every time you do an encounter, if you do not get a shiny, for 3 total checks in just one. The second is the Masuda method, which was introduced in Generation 4, which involves breeding 2 Pokemon from different regions. The generated egg will have a 5 to 6 times chance of being shiny depending on the generation. Generally, there are a few basic ways people may hunt a shiny Pokemon. The first is simply running around wild grass and doing encounters until a shiny Pokemon appears. The other is known as a soft reset hunt, and can only be done for certain Pokemon. This involves saving in front of a certain encounter and starting it over and over until it finally generates a shiny. How do lines of code such as a video game determine a random result? The truth is, it doesn't. Most games determine randomness by reading from a long list of numbers. An easy example of this is if I had a random event that had 6 different outcomes, such as a 6-sided die, I could use the repeated decimals of 1 over 7 as results, since 1 over 7 is equal to 0.142857, and that repeats, and map each number to one of my outcomes. Only one outcome is rolled, then it will just go to the next digit in my list. After 6 encounters, it resets and repeats. Using a pre-made number or generating one like this is called a seed, and is what allows games to create what we refer to as pseudo-randomness, which results in the random number generation we need, which I will simply call RNG from now on. The RNG from my earlier example is easily noticeable for a few reasons. Let's say 2 people play the game at the same time and notice that they get result A from the first random counter since they are on the first digit of my 1 over 7 sequence. Well, this can be solved by using a secondary method to determine a random starting position in the sequence, maybe another repeating fraction or using the clock date of your computer or console. Great. Now 2 players will, most likely, get different results from their first random encounter. New problem. My seed randomly goes through the results in the same order every time. This means that if a player is attentive enough, they will notice this pattern and can easily predict the encounters. This can now be fixed in 3 different ways. We can either have the seed be reordered or generated differently every time it loops to avoid repetition, but this is slow and clunky for processing. An easier and more widely used method, at least for older games, is to keep the seed simple, but have it update often enough that no pattern is recognizable. The common method is to have the seed advance once every frame. This means there is no guarantee that the pattern will ever repeat itself and is back to being pseudo-random. The third option, which is a more nuclear one, is to not use rational numbers like 1 over 7, and instead use irrational numbers like square root of 2 and pi, as they will emulate randomness due to their endless non-pattern decimals. This option is a bit rough for games that need a lot of RNG, since the more decimals you generate, the slower generation will be. This may lead to games starting to run a bit slower the longer the playtime of a session is. Pokemon largely uses the second solution by generating a seed using the time and date down to the milliseconds of when you start the game up and advance the seed to the next hexadecimal number every frame. There are many resources going over how knowing this information still allows us to manipulate the RNG and guarantee certain results, like for example a shiny Pokemon with 6 perfect IVs in a specific nature, which would otherwise be a 0.0000000000032% chance. I'll put a link to I'm a Blissy's channel and video in the description, as I think they have a great set of in-depth videos for people interested in some more of the details of Pokemon RNG manipulation. When we discuss the RNG in Pokemon games deciding on a shiny Pokemon, we will simply assume the pseudo-randomness is irrelevant and it is true randomness. If we do and use the binomial distribution worked from above, the probability of getting a shiny on the nth encounter is the same as the probability of not getting a shiny up to the nth encounter, with soft reset and wild hunts, which can be written as 1 minus 1 minus q to the power of n, where q is our all too familiar 1 in 8,192, which is the number I'll focus on for simplicity. Now, one common confusion that comes from this is that the nth encounter has a unique probability tied to it by this equation. But in reality, whether it's your first encounter or 1,000,000th encounter, the true odds are still 1 in 8,192. The real information this formula and probability is telling us is simply the chances of how likely you are to do this many encounters without seeing a shiny Pokemon. If we revisit the coin joke from earlier, we can see it gives us a good idea of this. For us to match the odds of generating a shiny Pokemon, we would need to flip a coin 13 times and never once get tails. Even though it is a 50-50 chance every time we flip that coin, the odds of us going 13 coin flips in a row and they all end up heads is the impressively low odds of 1 in 8,192. So while it seems like as n increases, the probability will increase, the true odds are always 1 in 8,192. So no shiny is guaranteed, no matter how many encounters you do. There are two special exceptions to the basic probability formula we made above, found within Pokemon HeartGold and SoulSilver. While we assume the Shiny Charm and Masuda method are out of reach, RIP to DS Online services, we can still make pseudo-boosted probabilities. The first is selecting your starter. Usually when you select your starter Pokemon, you see the sprite of the Pokemon before your selection, so you can see what they look like. In every Pokemon game, it is just that, a loaded sprite. It's not the actual Pokemon. If you wanted a shiny hunt for a starter Pokemon, then you would need to select your starter, then either check it in the menu or start an encounter to check if it is shiny. This is true for every Pokemon game, except HeartGold and SoulSilver. The sprites shown when selecting your starter are the actual Pokemon you would receive if you would choose them. Now this is otherwise a pointless detail, as things like IVs, natures, and even genders, unless you're Torchic, are not visible on starter sprites. However, this means a lot for shiny hunting, as when you select the machine to choose your starter Pokemon, this means you actually check 3 Pokemon for every soft reset you do. We first need to realize that this actually means there are multiple possible ways you can get a shiny Pokemon. There is the obvious and most likely, you get a single shiny Totodile, Cyndaquil, or Chikorita. There's also the less likely outcome of getting multiple shinies in one encounter. This could either be 2 of the trio or all 3 are shiny. If we account for the 7 different cases and their own respective odds of occurring using the binomial distribution, then we get that the probability of a starter being shiny is 3q times 1 minus q squared plus 3q squared times 1 minus q plus q cubed, which can actually be simplified using the same equation from earlier, getting us 1 minus q to the power of 3. Again, using q is 1 in 8,192, we get a probability of 201,302,017 over 549,755,813,888, which is roughly 1 in 2,731, or 0.0366%. This is roughly 3 times more likely than the usual odds of obtaining a shiny if we could only check 1 at a time. The second comes from HeartGold and SoulSilver's very own child gambling game. Welcome to Voltorb Flip, but we actually just care about the prize corner where you can spend the coins you earn from Voltorb Flip. If you have enough coins to purchase 5 prize Pokemon, as that is the most you can purchase at a time, then this allows you to check 5 Pokemon with just 1 soft reset. Just like the starter Pokemon situation, since this is a simultaneous check, there are multiple situations where a shiny is generated. We can use our combinations and binomial formula to make the following equation, where T is simply the odds of not getting a shiny Pokemon. This is roughly 1 in 1,638, or 0.061% instead, which is around 5 times more likely. Note this can also be simplified the same way we did for the shiny starter equation earlier. Since there are different odds or ways to hunt for a shiny, we will slightly rewrite our earlier equation for odds of seeing a shiny after n encounters, where p is the probability of the specific hunting method. Now to continue from here, we will need data. The amount of encounters it took for each person to see just how likely their shiny encounters were. Thankfully, a few YouTubers have done a silly little challenge in the exact game we just talked about, where they only use shiny Pokemon to beat the game. They used the encounter numbers from SmallAnt's run, as many others did not actually keep track of their exact number of encounters, it seems. Not pointing any fingers. Using a spreadsheet and calculating the number of encounters for each method, here are the results of SmallAnt's run. We can say the first 2 Pokemon are decently lucky, being well below 50% odds, Ignoring is guaranteed Gyarados shiny, another benefit to doing this run in HeartGold and SoulSilver. However, what is insane is the unfortunate tale of Gert the Electrode taking well over 50% at around 81% odds if we ignore his missed shiny partway through, which would have landed him on around 78% instead. Not much better. This pales in comparison to the insane luck he gets from here on out. He must have prayed to Fortuna and received the boon, as he proceeds to never go above 500 encounters for the next 3 Pokemon he hunts, getting 0.24% for Dratini, 3.48% for Lugia, and 4.87% for Ho-Oh.
Now, this is great and all, but I hear what you're saying. Only 7 Pokemon with data to go off of, and one of them wasn't even a proper hunt. Thank you for the comment. Please, feel free to pause the video now and type that in the comments. Did you do that? Good. Because now you will feel silly once I tell you that I didn't just get 6 data points, omitting Gyarados. I got 15. Now you may be asking yourself, whoa, now you're lying to us. You said you couldn't find other YouTubers with exact encounter numbers. I promise you, I didn't lie. I actually did struggle to find other YouTubers' data to use for this bit at the end. But I never said that I didn't. That's right. I went on a long and arduous journey myself to do this, and can I just say once again that SmallAnt's luck was insane to think about now doing this myself. I can only imagine the amount of hours he saved on those last 3 hunts.
Here are my results of doing this. You will of course see that I also did the Gyarados, this time for personal reasons as it plays no part in the data. 2 other things you will note is I made use of the game corner hunting method 3 separate times for 2 EVs and a Sandshrew. The other is Sudowoodo. If I recall correctly, it's been about a year since, I started to hunt it normally, but then decided to extend this data collection to also explore RNG manipulation. So using the aforementioned YouTube tutorials from Blissey and a few others, I was able to force a shiny Sudowoodo. This is also why the data is unknown, as I did not think about writing it down back then, and RNG manipulation requires me to edit the date. Oh, another thing to note, if you are wondering why the nicknames are not shown this time around, it's because I named each shiny after a friend of mine in a group server, and I don't want to dox them. Now, those pieces out of the way, let's look at the numbers themselves. My starter and Sandshrew encounters were sadly not properly counted, so I used an estimated amount based on time taken per encounter and total time taken. This is obviously not perfectly accurate, notice the wide range for the starter, but it will get the job done for now. We were decently under odds for our starter, but well over odds on the Sandshrew. These were both hunts done with boosted odds, starter hunt and game corner hunt, so my hopes are a bit rough here for the rest of this challenge. Around here is where I tried to speed myself up, getting both the guaranteed Gyarados as well as doing the RNG manipulation for Sudowoodo. Afterwards, I did the same Electrode hunt that SmallAnt did in his video, since I thought the shiny looked cool and the time per encounter was incredibly fast. Thankfully, I did not repeat Gert and got it just a bit below 50% odds. The next notable hunt was for a shiny Skarmory. This one was special, as I abused a certain overworld ability of Magnet Pull, which increases the odds of you finding a Steel type when a Pokemon with that ability is the lead. Combine that with my random Magneton also being a certain level and using Repel, I would guarantee that the only wild encounter was a Skarmory. I was able to go well under the odds here at less than 10%. This next one is quite interesting to me, as both SmallAnt and I got a shiny Lugia in a significantly small amount of encounters. What is strange is that this was actually my second try at doing this challenge. I had gotten around 8 or so shinies back in 2022. Back then I believe 2 or 3 I used RNG manipulation for, so honestly I'm kind of happy I had to restart. But a broken hard drive made me lose the save file on my computer, and so I had to start fresh. If my memory of that lost run serves me right, I properly hunted Lugia and was also around 100 to 200 counters then too. Maybe Lugia and Ho-Oh have secretly increased shiny odds in these games? I doubt it, considering how much other communities have dug through the code of these games. It may still just be a strange coincidence. From here, I went on my worst hunt, the first EV of 2. I did both EVs at the game corner, and not like SmallAnt did for his cream. Phrasing. This means I once again had the approximately quintupled odds of getting a shiny. Despite this, I had my longest hunt yet at around 81% odds. This is insane to me that both my game corner hunts so far had been my worst hunts by far, despite them being probabilistically my easiest ones. However, Fortuna smiled upon me that day too. After receiving the first EV, I went back to Voltorb Flip, got back up to 50,000 coins, and then after only 3 encounters, so 15 EVs total, I got EV number 2. This is an insanely lucky find to happen. Only 3 encounters at the previous one. which is a roughly 1 in 26,889 chance, or 0.0000372% chance. It was a nice break up to the lengthy endurance run that the first EV was. After this, I just resigned to doing some simple running around in Wildgrass to close it out. This meant I did not actually control which shiny I got, and it was a purely random way to close out this challenge. The first one came in slightly below odds with Giraffe Rig on Route 48, just below the Safari Zone at 47%. At this point, I proceeded to spend a lot more time on the challenge, realizing just how close I was to finally completing this now 3-year-long effort, and was able to go on another route, Burn Tower, to get my final shiny in Coughing at decently below odds of 35%. Now, if you're thinking this sounds like a fun thing to try and do yourself, I would strongly advise against it. By estimating the time it takes for each soft reset and each wild encounter, I was able to estimate that I had spent roughly 30 days of real-life time doing this. I repeat, real time. This isn't an hour to a day for 30 days, this is around 700 hours of shiny hunting. This was not something for the faint of heart, so be cautious if this is something you are thinking you want to try. Maybe just try a newer game or a ROM hack with increased shiny odds, like Ludlock or something. Thank you all for watching this video. If you watched this far, then I am sure you realize this was a long effort in the making. Feel free to leave actual comments below, not just the joke comment from earlier, about the video. Any feedback is of course welcome. Not sure if I will do any more educational mathematics and games videos, but this was at least an interesting project to work on over the past while, so I hope you enjoyed it and learned something about probabilities and how video games create randomness.